A pedigree is a family tree, and it can be used to track the inheritance of a characteristic through a family. There's certain rules that we need to follow when we draw a pedigree. Firstly, the females are the circles and the squares are the males. If somebody actually has the characteristic that we are following, we actually shade the whole thing. So they have the characteristic tongue rolling or cystic fibrosis or whatever it is that we're following. Okay, they have the trait. Now, often we also demonstrate that if they are a carrier of the allele for the trait but don't actually have it themselves, we can shade half of it in like this. Okay, next. This line here means a union between the female and the male, you know, and they've had offspring. So their offspring is in the next row. Okay, so one generation per row. And we put them in birth order from left to right. Now here you can see that this male has had offspring with this female. Okay, and then there's their children, 2 females, and then this child has had offspring with this gentleman here. So what I'm going to do now is colour in a particular characteristic that we're going to look at, and in this case it's cystic fibrosis. Now, cystic fibrosis is a condition. Cystic fibrosis. Cystic fibrosis is a severe autosomal recessive disease. Autosomal, it means that it's on one of the 22 chromosomes but not the sex chromosomes, and obviously it's a recessive gene. It's a condition that affects the production of mucus, and so people with cystic fibrosis produce a tremendous amount of very thick mucus in their lungs, and subsequently they have lots of respiratory and breathing problems. They have lots of respiratory infections, and that puts a lot of strain on their heart and on their lungs. They also have some problems in their digestive system as well. And look, it's another life-limiting condition, cystic fibrosis. The treatment's got much better, but people generally do have a shortened lifespan as well. Okay, so it's autosomal recessive. I'm going to go ahead and colour in the people who actually suffer from cystic fibrosis. And from this, we're able to go back and work out what the genotype is going to be for everybody here in the pedigree. And remember, of course, that the phenotype here is cystic fibrosis. So the people who actually suffer from cystic fibrosis, that's the phenotype. All right, now, so it's easiest for us to start with this by saying who has actually got the disorder. Now, so we're going to go for, I'm actually going to go ahead and do A, because A, capital A and small a look different. So A means that it's the normal, healthy allele. Okay, and the small a is the cystic fibrosis. So they're actually, it's the gene that contains the disease for cystic fibrosis allele. Okay, so look, in terms of the symbol that you do, it's kind of arbitrary. Pick something that's easy to see the difference. So if you go for a capital S and a small s, it's hard to tell the difference. So A and A, let's do it this way. All right, so somebody who actually has the disorder must be the 2 recessive, homozygous recessive. So they're going to be the small a, small a. We can say that for sure, we can do that for all of them. Okay. Next, for this person to inherit the cystic fibrosis allele, they must have got it from their parents. So their parents must have one allele that's affected. But they don't have cystic fibrosis. So that means they must also have one normal allele. So that's their genotype. Okay, now, so this person here also has it. So the mother must have a small a, or the cystic fibrosis allele, but also we can go ahead and put a capital A there because they don't have the condition. All of these others we can say, I should have put that one at the bottom, must have at least one capital A, and because they don't actually have the disorder themselves, so we can go ahead and put capital A's here for all of the ones that don't actually have the disorder. Alright, can we do any more? Sometimes we get to a point where we can't, and we have to just put question marks in. We can't say for sure any more than this. But let's have a look. These two parents are like this, aren't they? So they're so you could have this genotype. So you could have this genotype. So this person here, we can't say whether they're big A, or big A, little a. So I'm going to put a question mark here for the second allele. And that it goes the same for this person here. That's okay. Now, here, if I can just go ahead and do another small little Punnett square, you can see how valuable Punnett squares are from time to time. Beg your pardon, if you get it right. So that is the female, and then the male is here. So we have either, it's helpful if you get it right. Okay, we've only got two choices here. We have got big A, or little a, little a. So we know that they've got a big A, so they must also have, actually, can we say for this person, yes, we can say for this person, but forget about them for now. Let's do this one. This person here has got these parents. Big A, little a, little a, little a. So this person here must be big A, little a. This person is a ringing, and so they're married into the family. Now, but they have had an offspring that is little a, little a. So they must have got the diseased allele from this person here. So that person was a carrier, and they had an offspring with somebody who has cystic fibrosis, and so that's why they have a child that's got it. Okay, now can we say for sure whether these two are carriers or not? What's the situation? Have we done this one before? It's this one here, isn't it? So one parent is big A, little a, and one parent is little a, little a. So what are our options? They either have the condition, like this person, or they're carriers. So we've done every single one of them except for these two here we just weren't able to say. Pedigrees are really helpful, and doctors actually use pedigrees when they're trying to look at the family history, trying to identify if something is, say, a sex-linked, recessive disorder, and also to work out if, say, a child is a carrier and whether they've got the potential to pass that gene on to their offspring. So they can be very, very helpful.